Swayam Prabha. Digital India. Educated India.
So let's first do it for x. So x and y arise from a coin toss each, independent coin toss. So we have done this computation. What was the expectation value of x square? Anybody? P. Expectation value of x is also P, but that is squared. Okay, kappa 3 of x, let's do that. I will use this form and simplify it further. This, you can see expectation value of x is what I called mu. So it's 3 mu square minus mu cubed, minus plus 2 mu cubed. So expectation value of x cubed minus 3 expectation value of x, expectation value of x square. This is an easier way of writing. What is the expectation value of x cubed? P. This is P, this is also P. Okay. So now comes the, we have computed it for one coin toss, and I said we will take x and y, we can, what is the value for two coin tosses? Okay. The answer is very easy. So let's do that. I mean, why should I do it for just two coin tosses? I'll do it for n coin tosses, which is the binomial distribution. So I won't do it for two. I'm brave now. All n coin tosses, they are all independent of each other. You can see we can use this property of cumulants recursively, and how do you understand this? I can think of this as my first and then write it as cumulant of this plus cumulant of the rest. Keep doing recursively, you can show that cumulants add completely. Not just for 2, 100 of them, you add the cumulants. Now comes the punchline. These were all numbers, right? All of them are identical coin tosses, identical coins. So each one of them will give the same answer. It's important. So it just scales nicely. So now we know the results for kappa 1, kappa 2, kappa 3. We know the answers for n coin tosses, just multiplied by n because of the additivity. Now you can turn this around and we want to ask, for instance, so for let's look at kappa 2, which is the variance, sigma of z square and variance was things, formulae that you know. NPQ, in books they write 1 minus P as Q. Yeah. Not you.
So we know that like x1, x2, etc. I mean till xn are independent of each other and they are not equal. Probably they could be equal. They couldn't be equal.
They are identical. I am assuming they are identical coins. Otherwise, I can't write n times.
That's what I thought.
Yeah, I am assuming extra. If they were not identical, then you just add the answers for each.
No, how do we know it they are identical?
No. I am defining it to be so. That's the binomial. That's how we got the binomial story. Yeah.
So for a single coin toss, taking X or Y, it was easy to compute the expectation. But when it comes 0, 1, 2, we assume 2 variables.
No, you can forget about Z and you can do it with one variable, right? So the probability of getting 0 will be P square. Probability of getting this will be 2P into 1 minus P. Or the other way around, is it? We know how to compute it by hand. We know how to do this by hand. So in principle, I can compute the variance without using X and Y. But since I know cumulants, life is easier. I don't have to go through this step. I am skipping this whole step. Okay? So go back and you can do this. You can check. You can check for the third cumulant, it will be n into p into 1 minus p into 1 minus 2p. And you can turn that around and compute expectation value of z cubed, expectation value of z square, all those things. You can compute by inverting this formula. You can do that also. Okay? So this is just something I wanted to show you. My goal is really for you to learn two things from this. Why variance is defined as it is. Number two, that there exists an infinite set of those guys, of which the tip of the iceberg or whatever is mu and sigma square. Okay, and for purposes of grades, which is very, very highly important and seems to be the ultimate goal in Indian education system, which is annoying for a teacher, but that's how it is. Then you don't even have to worry about kappa 3 or whatever. Stop at sigma square. But I hope people at RSIC have more spark than that and you are interested. I mean, sometimes as Professor Balke says, you got to show people that what you know is the tip of the iceberg. And I'm telling you what is underneath. And it's for you to explore, not for me. Okay? So now let's just work on a physics problem. And the physics problem I'll state as follows. I have a large volume V. It's a big volume. Shape is not important. It has n particles of mass, identical. So if you want a picture, think of it as a gas of hydrogen, nitrogen, whatever your favorite gas. Monatomic, atomic if you want, diatomic, tri, whatever. It's not important for me. It's just that they're all identical. It's not a mixture. It could be a mixture, but I'm not. This is this thing. So we can associate a number density. So let rho be, so this is like the average number density of the particles. Okay. But we all know what's happening inside. Particles are not just it's not like they are sitting in, if you put a cube of ice in and temperature is below freezing, it will remain so. But in a gas, that's not what is happening. Particles are moving, there are collisions happening, their velocities are changing after a collision, before, after. So it's getting really, it's a very active system which we can't see. What we perceive is that there is an average density out here. Is this clear? The setup. So we are going to assume rho n and v are large, but this quantity rho is some fixed. So if I want to, I can do the following thing, I can double my volume, but then I have to also double the number of particles so that this quantity is still, okay. So this is very, very large. Now I'll do the following thing, I will take a small volume, little v, and I start at any point in time, I will observe how many particles, I'll start counting how many particles of the gas are in there. Suppose I have some way of counting, okay. First question to you is, will the number of particles in this volume, so again you may say, how can this be so? I mean, what I am saying here is, first thing is that there are Avogadro number of particles. V could be, order of liters, but if this is like even milliliters or whatever, it will still have, I mean, it could be so small that you can have 1000 particles, say, typically. So, and that will be small enough. Okay, so this is our sample volume. Question to you is, will the number be the same? No. Why? Volume is fixed, but I am counting exact number. I'll stop my watch. This second I'll count. Wait 1 second. Later again count. They are constantly moving. So particles are coming in, going out, etc. So the number of particles in there is like a random variable. Okay. So Nm denote the number of particles in the small volume. So I have done m measurements in time. Okay, so now this is one thing. Then we can ask, what is the average number of particles? Right? What would be the average number of particles? What should I do? So let's use symbol and write. I'll put T out here. And what is our intuition? What should this be equal to? Rho v. That's our intuition. It should be that. Now I'll ask you, what about, this is a series, what about standard deviation? What should it be? We can define it from statistics or from our way, we can define it, right? So here what we would do, we would define, you can just go ahead and do the same thing we would have done. You can define, I won't do this, okay? So this is one experiment, and this, I put a T out here to remind me that it is time average. So I picked one particular volume and then I averaged. The second experiment is, I pick n similar volumes So now I do something different. I pick one like this, I do one more, I pick somewhere else, I pick m, I same capital M number of them, but at same time I measure. Okay, again yeah, somebody was asking something. Yeah.
All these small v are of equal size. If we pick n volumes, would each have one?
M,
Or like half, because capital in identical particles are only there.
but M is much, much small.
You have to take it in.
Thanks. I wrote later also N1 to NM. Yeah. Sorry. Yeah, I don't pick. So M will not be Avogadro's number. This is like 10 power 23. M might be 100 or something. Okay. So is this clear? Again, I can define, I'll call this is time average. And I'll call the other one ensemble average. I defined ensemble for you. E.
Sir, what does the hash denote?
Huh?
Hash, what does denote?
Number. Sorry, American style. Americans use hash for number. My fault. Not allowed. What do you expect the ensemble average to be? Rho V. Again, this is expected. Okay, good. So we know this. It's an expectation, and our expectations are quite this thing. We expect these two to give the same average, time average equal to ensemble average, and it turns out that there are some. First thing is that for this to be equal, your system should be in what is called thermal equilibrium. Number one. Okay, so first thing is that it shouldn't be that if I measure this at one instant, I get something, I get an average, another instant, I'll get something else. So we expect averages to be independent of time, and we expect time average to be equal to ensemble average. So these expectations are not always satisfied. Okay, so one has to remember this, but our intuition says that these two should be equal, etc. And it works most of the time, and it's also interesting when it doesn't work. Okay, but we are at the level where we'll assume that ensemble average equal to time average. Okay, so there are, technical conditions under which these two will be equal, but that's too technical even for me to state it. Is this clear? I'll lift it up.
Sir,
Yeah, go ahead.
so definition wise, fundamentally what will be the difference between a time average and an ensemble
I
average?
explained to you, that's all. It's like copies. You make, it's really in your mind, you could even think of making copies. That's all.
Sir, the row V, shouldn't it be capital V because the small one?
No, rho V will give you the number of particles. If it is capital V, it will give you a capital N,
Okay, so we need
which is only a small fraction will be there. So rho times little v is what will tell you how many particles we expect on an average. But we want to model it, we want to ask what is the variance, what is the, we think of it now as a random variable, and now I need to ask what is the best, can I write a probability distribution for it, which will satisfy our things, and we will do that. Okay, so we will map it to the coin toss problem now. This is what I am going to do now. I'll map this. Okay. So let's we'll stick to the time average for now, and we'll pick a particular volume. Okay, we'll stick to the time average, and so we have this picture. I'll just draw a square now. Okay, so this is capital B, this is little v, and we think of each of the atoms, large number of atoms n, as being simulating a coin toss for us. If you pick one particle, it's either in V or not in V. Okay, so let little p denote the probability of finding a given particle So there are many particles, and of course we cannot name them like we name our cats and dogs, okay. But let's say we named one guy, we colored one of those items and we're tracking that guy. Let P denote that probability of finding the given particle in little v, in this cube. What is the probability we should assign? What should little p be? That's a nice choice. Any ideas? Yeah. She says 1 by 2 and you're saying v by v. Because this is so small, it's not this is one of those cases where it is not a fair coin toss. The chances of not finding the particle outside is much larger than inside because this is very small. We are going to assume that v by capital V is like, some 10 power minus 10, okay, some large number. So natural one is this. Because it also says, right, if you double the volume, if you make it 2v, the probability also scales. So it should be like this. So this is the, okay, so this is the probability that we are going to do. Okay, but now we have capital N particles, N is 10 power 24 or whatever, right, or 10 power 23. It looks very complicated, but now we know, it's like if you know answer for one coin toss, we know how to handle other things also, right? So N being large doesn't matter, we can work with the cumulants, we can say a lot of properties of this thing, okay? So now we can ask, we have the probability, we mapped it to a binomial process and there are N particles. Each of them are independent of each other, okay? So, okay, M can go in principle from 0 up to capital N, okay. But N is so large, we can even think of it as infinity even. But right now we won't. So what is P of M? N choose M. And all the other particles should be outside. This is the binomial thing which we wrote last time. So what we have done is nicely to map this to the binomial problem. But this is still not nice because what we would like really is a limit where v and n go to infinity such that rho is kept constant. Okay, so physics is telling us okay. So we want our results to be independent of really n and v and only depend on the ratio rho. This is called the thermodynamic limit or the large volume limit. So this is a limit which is being told from physics. Okay. So let's look at this. So what it says is that let's take that limit on P. What is NP? Okay, so what it says, you can see here that if you're taking v to infinity, p is going to 0, but the product NP is kept constant and is equal to rho v. So a mathematician will never go through this process, he will say I will take n to infinity, p to 0 such that NP equal to some constant which they will call lambda. Okay, but this is physics giving you the input. So now what I want to do is to implement this limit on this probability distribution. That's what I want to do. So this is a good place to ask questions as I'm erasing this board. Okay. So we want to take the thermodynamic limit on that formula. So I will rewrite P of m in the following way. Okay. So first thing is that m is some finite value, but n is going to infinity. So I can approximate this by n. I can drop the 1 and m plus 1 here. So this is approximately n power m p power n I'm okay with this because NP we know is going to constant in the thermodynamic limit. So this term is taken care of, but we have to still do something here. Okay, so let's do that as follows. We write this as so I've done the approximation, I've thrown this away. Again here also I'll do some approximation. M is some finite number. Okay, n is going to infinity, so this is approximately 1 minus p power n. Okay, it's a good, it becomes better and better approximation as n becomes larger and larger. Okay, so this is nothing but rho v. Question here is, what is this? So this is a finite number, this is going to 0, but there are infinite number of terms. Does anybody know what this limit is? If you don't know this, I'll just take the formula. It's equal to e power minus x. Okay, so this will become e power minus np, which is e power minus. What is this distribution? Have you seen this? This is the Poisson distribution. With lambda, which I wrote. Okay, I'll give you an exercise. All cumulants for the Poisson distribution are lambda. So in particular, kappa 1, kappa 2, kappa 3 is x, is lambda itself. You can compute this, do calculations and prove it. Okay, I stopped at kappa of 3. You can do this calculation. Okay. So what we see is that a priori thought that, you know, the binomial and Poisson were like two different things, and we are seeing that in a nice physical situation, what is very natural to the problem is the Poisson distribution, not really binomial, even though we started from there. And this is not a limit we would have thought of, because like she said, P is equal to half, that is our happy hunting ground, correct? So the whole point here is that this is what comes very, very naturally. So actually I need another half an hour to discuss the other continuous distribution which comes. So I'll just tell you the answer, but we can derive it with our limited understanding. So again I'll pause here. Is this clear what we have done? So we have created a mathematical model. Even though we know nothing about the gas, we are just able to make this nice statement. Just few inputs, we are able to come up with the density fluctuation. So now we can ask, what is the variance? It is lambda. Or what is the number? Fluctuation is going like root. So sigma goes like root rho v. Important. So the thing is that it says that the average number of particles is rho v, but the fluctuations about that will go like root rho v. So suppose you know mu is like 100, then it tells you that sigma, the variance is 10. Okay, so that's like roughly the error. I mean, you will find that I mean, you can make this very, very precise, but I mean that is if you make a measurement, those M1, M2, M3, they will have variance 10. In other words, most of your numbers will lie between 100 minus 10 and 100 plus 10. Okay, that's what it means. So,
Sir,
yeah.
sir, in the exercise that you have written, what is x supposed to be? Is it some random variable in a Poisson distribution? Okay. Okay,
With
sir.
parameter lambda. I computed for the I only computed it for the case of what do you call binomial. This I didn't do. But you can, I mean, we can do simple check, remember? This was the variance. So if you took, you know, n going to infinity, p going to 0, we will have this fellow, this will go to rho v or lambda, p will go to 0, so it goes to lambda. So we can derive it from taking the thermodynamic limit of, so you can get kappa 3 by cheating, it's not cheating, to take the thermodynamic limit of kappa 3 because you wrote the answer. Again, that was what n into p into 1 minus p. Basically, it says throw all these things out and this is lambda. Okay. So, the setup is the same, but now we want to ask, the question we would like to ask is, what is the distribution of velocities of the particles? Okay. Now, again we can do the following thing. We can pick tag one particle. If you like it, give it a name and follow that particle. And if you follow it in time, you know, between collisions, of course, its velocity will be constant. And then after collision, its velocity will change. Okay, and so on and so forth. So if you're looking at time scales where multiple collisions happen, okay, you're making measurements like, you know, between 100 collisions. First you make one measurement, second measurement after 100 collisions, third, I mean, not even, you don't go by 100 collisions, but roughly 100 collisions happen, something like that. So what you will see is that if you pick that the velocity of the particle will be a random variable. Okay, so first thing is to tell you is that this is nicely modeled by some probability. But now, unlike the case of coin tossing, Vx, Vy, Vz can take values in the real line. Correct? So, we could ask what is that is, so this guy is like a cube with sides delta v in the velocity space with sides Vx, delta Vx, delta Vy, delta Vz. Inside that volume, there is some probability if you sum over that. It's a higher dimensional generalization, but doesn't matter, it's just this, and total probability over the full volume should be 1 because it's in the volume, right? So this is, so a question here is, what should this be, this quantity? First thing is that even if you look at collisions, you've done conservation of momentum, right? In any collision, what happens? The x momentum or x velocity is conserved. Why? They are independent of each other. So we will expect that whatever Vx changes, Vy and Vz, they are independent of each other. That could be that will be our guess. Okay, so this is being joint probability of all these things, they are independent of each other. That means they depend only on, I'll call this P tilde Vx, and I'm doing one cheat here. I'm saying Vx, Vy, Vz, there's nothing special about x, y and z, right? So I should use the same function. It shouldn't be different functions. That's not, I mean, x direction is not going to be different from y. So this is what it says. So it boils down to saying that this answer must depend only on Vx. This thing should depend only on Vy. This should only depend on this thing, and these three are the same function. So now I reduce this problem to finding this function. But there's another point, is that x, y, z is some arbitrary coordinate system. I can choose someone else can come and what is your x-axis need not agree with mine. I can do anything I want, and there's no particular direction. Our volume is so big that there's no preferred direction. So then we would expect that this should be some other function of only v square. This is called isotropy, no preferred direction, because this is the only combination which doesn't depend, it depends only on the magnitude under its invariant. So we have extra property that this quantity should be writable as a product of three functions which are identical, and also writable as a p of v square. Some function, we don't know these two functions. It turns out that this requirement force fixes the answer for you, and I'll write the answer. Yeah, I'm done in 1 minute. Who is waiting? I'll be done in 1 minute. Some constant which I think you know from last lecture, but I'll write this. Okay, so this function is nothing but, first thing is v square, you can see is vx square plus vy square plus vz square, so it satisfies this property. Okay, mean is 0, that means there's no drift, nothing, all directions are okay, but it has a variance, and that variance is what we call the temperature of the gas. And these are constants, this Boltzmann's constant, and this is the mass. Okay, so actually, I mean, it takes half a lecture to prove that this implies this. It doesn't tell you what this number alpha sigma square is, but this is physics. This is math. Mathematics of saying this should be equal to this. This is the only function which satisfies that property. And then physics tells you, that's actually giving you the temperature of the gas. So it says that if your gas is hotter, the velocities will be, the fluctuation will be more. Okay. So thank you, and I'll just wind up.